Everyone. Welcome back to another lesson in MCV4U. Today we'll be looking at the curve sketching algorithm. So the first derivative and the second derivative provide information about the shape of the graph. As each information is obtained, use it to help build the sketch. So the first thing we want to do here is we want to use the function to determine the domain and anti-discontinuities, determine the intercepts, find any asymptotes, then determine the general shape of the curve, if possible. Once we get that information, we want to move on to the first derivative. The first derivative helps us find the critical points where the derivative is equal to 0 or undefined, determine where the function is increasing, that's when f prime of x is greater than 0, and where it is decreasing, when f prime of x is less than 0. And here we're going to identify, again, any local maxima or minimum. If f prime of c is equal to 0 and f prime of x changes from negative to positive at c, then f of c is a local min. If f prime of c is equal to 0 and f prime of x changes from positive to negative at c, then f of c is a local max. Once we find this information using the first derivative, then we can use the second derivative to find the last pieces of information here. Again, we can determine any points where the second derivative is equal to 0 or undefined. Determine where the graph is concave up, so when the second derivative is greater than 0, and where it's concave down when the second derivative is less than 0. And then there we can determine, again, if there's any points of inflection where it changes from concave up to concave down and vice versa. And here again, second derivative can also be used to identify local and maximum minimum. However, this step here is usually not needed because it's already found with the first derivative. So usually don't need since already found with first derivative. However, again, if you want to confirm the function using the second derivative, again, if f prime of c is equal to 0 and f double prime of c is greater than 0, then f of c is the local minimum. If f prime of c is equal to 0 and f double prime of c is less than 0, then f of c is a local maximum. Then if f prime of c is equal to 0 and if f double prime of c is equal to 0, then the test is inconclusive and the first derivative must be used to make conclusions. Once you get this information from the function, the first derivative, and the second derivative, you can use all that information above to sketch the graph. And just a note here at the bottom, again, you will not always use all the steps in every situation, and use only the steps necessary to give you a good idea of what the graph will look like. And so let's use this idea of the algorithm for the function, the first derivative, and the second derivative to apply it to a few examples here as well. So example 1 here says use the algorithm for curve sketching to sketch the graph of f of x is equal to negative x cubed plus 6x squared minus 9x. And the first thing we're going to do here is we're going to look at the function itself. So here we have f of x. Here what we're going to do is we're going to simplify this expression and we're going to factor out a negative x. If we factor out a negative x here, we have x squared minus 6x plus 9. And here, see that since it's a polynomial, we know that the domain in this situation will be x is an element of all real numbers. Here we get, if we factor out the x squared minus 6x plus 9, we see that's perfect square trinomial. So that will give us x minus 3 squared. Here, if we look at our x-intercepts, we see that negative x is equal to 0. Therefore, we know that x is equal to 0. That's order 1. And we also know that x minus 3 is equal to 0, or x is equal to 3. And that will be order 2. And here, our y-intercepts, or y-intercept, in this situation will be at 0 and 0. And so here we can see in terms of our function, f of x is equal to negative x cubed plus 6x squared minus 9x. See here that there's a negative leading coefficient, and it is degree 3. With that information, we know that it goes from quadrant 2 to quadrant 4. Starts in quadrant 2 and ends in quadrant 4. So that's the information that we were able to find from the function itself. And now we're going to move on to the first derivative. And so here we get f prime of x. So we'll derive the function. And f prime of x is equal to negative 3x squared plus 12x minus 9. Here we can factor out a negative 3. And we'll be left with x squared plus 6x minus 3. Here we can simplify x squared plus 6x minus 3. We can factor, and we'll get x minus 3, x minus 1. And so here we see again that f prime of x is equal to 0 when x is equal to 3 and x is equal to 1. And f prime of x here is never undefined. Okay, so now we'll draw our number line on our chart. So we'll go from again, negative infinity to positive infinity. And we'll place our critical points on it as well. So negative infinity to 1, 1 to 3, and 3 to positive infinity. So here we'll sub in a point that's less than 1 here. So let's say 0. So here the negative 3 is negative. 0 minus 3 will give us negative, and 0 minus 1 also give us negative. Negative times negative times negative give us a negative value, which means that here it is decreasing from negative infinity to 1. Now let's sub in a value from 1 to 3. Let's say that's 2. So here, negative 3 is still negative. 2 minus 3 is negative, and 2 minus 1 here is positive. So negative times negative gives a positive times a positive will give us a positive value here. So from 1 to 3, it is increasing. Finally, from 3 to positive infinity, this interval. So the point we'll sub in 4, for example, negative 3, negative, 4 minus 3, positive, and 4 minus 1 is positive. So negative times positive give us a negative value here. Oop, give us negative value here, which means that is decreasing. And so we see from negative infinity to 1, it is negative. That's right. So it's negative. From 1 to 3, it is positive, which is increasing. And then from 3 to positive infinity, it is decreasing. And what we can take from that is that at 1, there's a local minimum. There's a local minimum at 1, and we're going to sub in 1 into our equation to see where the y value is. So here we have f of 1 is equal to negative 1 cubed plus 6 times 1 squared minus 9. So here we'll have negative 1 plus 6 minus 9, which is equal to negative 4. So here we have a local minimum at 1 and negative 4. And here at 3, we see that we can sub in value of 3. So we'll see that when we sub that in, we have a local max at 3 and 0. Here, sub that in just to show that, and f of 0 is equal to negative, oh sorry, f of 3 is equal to negative 3 cubed plus 6 times 3 squared minus 9, which is equal to negative 27 plus 54 minus 27. 54 minus 54 is equal to 0. And so here, we do our second derivative now. Line to distinguish that. And so here, if we find our second derivative, that'll be equal to negative 6x plus 12. Factor out a negative 6, x plus, or sorry, x minus 2. And so here we see that f double prime of x is equal to 0 when x is equal to 2. And again, f of double prime of x is never undefined. So here we'll draw another number line. Negative infinity, positive infinity, and then our point here of 2. And so here we sub in 0, for example. So we sub in 0, we have negative times 0 minus 2, which is negative, positive, so that's concave up. Here, if we sub in 3, we have negative times 3 minus 2, which is positive here. So it's negative, so it'd be concave. So here, what we'll notice is that there's a point of inflection. Point of inflection at 2. And if we sub in 2 into our equation, so f2 is equal negative 8 plus 24 minus 8, and minus 18, sorry, which is equal to negative 2. So our point of inflection will be at 2 and negative 2. And so now with all that information, we can graph our function. So here we'll just label some of the axes here. So here, okay, so that's 2. So we're just labeling here again the x and y axis. It doesn't have to be exact here, as long as it matches the graph. So here we have our, if we look at our information that we're given, so if I zoom out here a little bit, so let's look at what information we're given. First, we know that we have a y-intercept at 0, 0. So let's put that at 0, 0. We know we have a couple of points from our first derivative. We know that we have a local min at 1 and -4. Let's write it out here. So 1 and -4. We have a point of inflection at 2 and -2. And we also have a local max at 3 and 0. Right? And so we know that from -infinity to 1, we see that it is decreasing. So if we draw this here, see that it's decreasing from -infinity to 1. Let's redraw this, sorry. Let's redraw this. So here, from -infinity to 1, it is decreasing. And from 1 to 3, it is increasing. And there's a point of inflection at 2 and -2. And then from 3 onwards to positive infinity, it is decreasing. Here we can see that based on our function, our first derivative and second derivative, we have a pretty good understanding of what the graph is supposed to look like. Okay, so let's look at example 2 here. It says sketch the graph of y is equal to 2x squared minus 6x minus 8 over x minus 3 squared. And we're given here the first derivative and the second derivative. So let's first look at our function itself. So here we get, if we write it out, we can rewrite it as y is equal to 2, so we'll factor out a 2 from the top, and we'll have x squared minus 3x minus 4 at the top. And at the bottom, we'll have still our x minus 3 squared. And so here, if we factor out our x squared minus 3x minus 4, we'll get 2x minus 4, x plus 1 over x minus 3 squared. And so there's a couple of pieces of information that we can take from this original function. You can see that we have a vertical asymptote at x is equal to 3. We have a horizontal asymptote y is equal to 2. we have two x-intercepts here. We have x-intercept at x is equal to 4 and x is equal to -1. And here we have a y-intercept and x is equal to 0. So if you sub in 0 to each of the x values, you get a y-intercept of y is equal to -8 over 9. Okay. And so here, what is interesting as well is if we look at our horizontal asymptote, we want to see again, does it cross this horizontal asymptote? Does it cross the horizontal asymptote? And so let's sub that in. So if we sub y is equal to 2, 2 is equal to 2x squared minus 6x minus 8 over x squared minus 6x plus 9. Okay, and so let's cross multiply. So multiply the 2 into the x squared minus 6x plus 9, 2x squared minus 12x plus 18 is equal to 2x squared minus 6x minus 8. Here, the 2x squares will cancel out. We simplify here. We'll get 26 is equal to 6x. And so 13 over 3 will be equal to x. And here, again, that means it crosses the horizontal asymptote at 13 over 3 and 2, or in a decimal approximately 4.3 and 2. So let's now look at our first derivative. So here we see that dy over dx, our first derivative, is equal to 0 when, so here 3x minus 17 is equal to 0, which sees that x is equal to 17 over 3. And so the first derivative is equal to 0 when x is approximately 5.76. And here we see that dy over dx is undefined when x is equal to 3. So here we have our critical points. Negative infinity to positive infinity. And our critical points are at 17 over 3 and 3. So negative infinity to 3, 3 to 17 over 3, and then 17 over 3 to infinity. So let's sub in a point 0 to, again, determine this interval from negative infinity to 3. So we sub in 0, -2, negative 3 times 0 minus 17, negative, and then 0 minus 3 cubed is still negative. And so negative times negative divided by negative will still give us negative value. And so here, from the interval of negative infinity to 3, it is decreasing. From 3 to 17 over 3, we'll pick a number in between, so 4. So -2, still negative. 3 times 4, 16. 3 times 4, 12. 12 minus 17 is still negative. And here, 4 minus 3 cubed. So 1 cubed is positive. So negative times negative divided by positive will give us a positive value, which means that it's increasing from 3 to 17 over 3. Then finally, value over 17, greater than 17 over 3. So let's say 6 here. Negative 2 is still negative. 3 times 6, 18 minus 17, positive. And here we got 6 minus 3, so 3 cubed is positive. And so here we see that it is negative times positive over positive, which means that it's negative and it is decreasing. Here, what we notice is, again, if we look at our original function, we have vertical asymptote here at x is equal to 3. And at 17 over 3, we see that there's a local max here. So there's a local max at 17 over 3. And so if we sub in 17 over 3 into our equation right here, 2, 17 over 3 minus 12 over 3 plus 17 over 3 plus 3 over 3. And so here we're just rewriting it so that it all, in terms of the original function of 2x minus 4x plus 1 over x minus 3, that everything is with a common denominator of 3, so it just makes it easier to calculate. And at the bottom we have 17 over 3 minus 9 over 3 squared. So we simplify that, we'll get 200 over 9 times 9 over 64. 264, we can simplify that. So if we simplify that there, we get 25 and 8. And here we can simplify that, and the 9s will cancel out. So here we'll get final answer of 25. And here we'll get a simplified 25 over 8. And so therefore, we see here we have a local max at 17 over 3 and 25 over 8. And that is approximately 5.67 and 3.13. And here, finally, with the second derivative, dy over dx2, that's equal to 0 when x is equal to 7. So here, we see that also the second derivative is undefined. when x is equal to 3. So here, if we draw another number line here, negative infinity to positive infinity, and our couple critical points, one at 3, over actually, one at 3, one at 7. So here, if we sub in 0, for example, value that's less than 3. So here, if we sub that in, we have 12, which is positive, times 0 minus 7, which is negative. And on the bottom, or the denominator, here we have 0 minus 3 to the power of 4. And so that would be positive. Positive times negative divided by positive give us negative value. And we can see that that would be concave down. Here from 3 to 7, we'll sub in a value like 4. So 12, that's positive. 4 minus 7, negative. And 4 minus 3 to the power of 4 will be positive. So here as well, this would be negative. This will be concave down. Okay. And then last value that's greater than 7. So 8, for example. 12 is still positive. Here, if we sub in 12 minus 7, that's positive. And then here, 8 minus 3 will be positive. So here, this is positive, which indicates that it's concave up. And so here are a few things we can understand. We know that at x is equal to 3, that's where the vertical asymptote is. And here we see that at x is equal to 7, there will be a point of inflection. So here we know that that's at 7. And here if we sub in f of 7 into the equation, so 2 times 7 minus 4, 7 plus 1 over 7 minus 3 squared. That'll give us 48 over 16, which is equal to 3. So we have a point of inflection at 7 and 3. Okay, so now we know a couple of points in our information that was provided from the original function, the first derivative, and the second derivative. Now we'll graph this. So first thing we'll do is we'll put some points on our axis. So and then also the negative values as well. Okay, and so a few things we can take a look at right from the beginning of the function. So let's zoom out here. So we see that there's a vertical asymptote at x is equal to 3. So let's draw that. Remember, we indicate asymptotes using these dotted lines. A vertical asymptote at x is equal to 3. Horizontal asymptote at y is equal to 2. And so let's take a look at a couple of pieces of information that we know. We also know that we have a y-intercept at 0 and -8/9. Here we can put that there. So that will be where our y-intercept is. We know that we have a couple of x-intercepts, one at -1. So we have -1 and 0, and we have another one at 4 and 0. Those are indicated there. So let me just actually label these. And a couple of other things that we know here is, again, that at 13/3 and 2, we know that that's where it's going to cross over the horizontal asymptote. So at 13/3 and 2, that's around 4.3, so a little bit over. That's where it's going to cross here at this point, 13/3 and 2. That's where it'll cross the horizontal asymptote. Okay, so let's draw this here. And so we know that from -infinity to 3, we know that it is going to be decreasing. And it passes through these points that we just drew. So that's going to be decreasing. So see that's decreasing. And it's concave down from -infinity to 3. Then we hit the vertical asymptote. And then here we see that it passes then through our x-intercept at 4 and 0. And then it'll pass through that point that we indicated, which crosses the horizontal asymptote by 13/3 and 2. And then we have a couple things that we know here. We know that we have a local max at 17/3 and 17/3 and 25/8. So about 5.767 and 3.13. So a little bit above here. So around this point. So where the local max is. So let's just drop that there. So around at this point, that's where our local max is, 17/3 and 25/8. And then we see that it's going to down. And there's a point of inflection at 7 and 3. So around here, so let me just indicate that at 7 and 3. That's where our point of inflection is. And so go back down and continue. And so our graph will look something like that. Okay, let's look at this last example here. And it's f of x is equal to x ln x. And so let's start with our f of x. And so here f of x is equal to, again, x ln x. And so let's see what we can find here. So when we look at our domain, we know for here, x is an element of real numbers. Because of the ln x, we know that here x has to be greater than 0. Our x-intercepts, we have 2 here. So for our x-intercepts, we have, if we make it equal to 0, 0 is equal to x ln x is equal to 0. This can't exist because it's outside the domain. And ln x is equal to 0. Which means that x is equal to 1. So we have an x-intercept at x is equal to 1. And here we have no y-intercepts. Okay, so if we find our first derivative here, using the product rule, so here we'll derive the x, which is 1, keep the ln x, and then f. And then the derivative of ln x is 1 over x. So that will be equal to ln x plus 1. When we simplify it, and so here we see that f prime of x is equal to 0 when, so if we make it equal to 0, we have negative 1 is equal to ln x. Here we can write it as e to the power of negative 1 is equal to x. And so 1 over e is equal to x. And you've put 1 over e into your calculator. It'll be approximately 0.37 is equal to x. Okay, so let's draw a number line here. So from negative infinity to positive infinity. And we have a value of 1 over e as our critical. And so we'll find a value that's less than 0.37. So let's say like 0.2. Sub that into our f prime of x. Sub that into f prime of x. Get a negative value. So here we'll see that it's decreasing. And a value that's greater than 0.37. So 1, we'll see that that's going to be positive. So it is increasing. So it's decreasing from negative infinity to 1 over e, and then it is increasing from 1 over e to infinity. And so here at 1 over e, I'm going to sub that back into our original equation. So 1 over e ln 1 over e. Here we have 1 over e ln e to the power of negative 1. Here, if we move e to the power of negative 1, we can rewrite it as negative 1 over e. So move the negative 1 to the front. Ln e by itself will just be equal to 1. So we have negative 1 over e. So therefore, we have a local min (1 over e) and negative 1 over e. And so that's approximately 0.37 and negative 0.37. And then if we derive the second derivative of ln x, or derive the first derivative again, ln x plus 1, our second derivative, that'll be equal to the derivative of ln x, which is 1 over x. And here we see that f prime of x will be undefined when x is equal to 0. Over here, x is equal to 0, that's out of the domain. Just remember, the domain is x has to be greater than 0. And so here, again, we see that it really only goes from 0 to positive infinity. So there's only one domain here. Oh, sorry, only one interval. So since it's really on one interval, if we sub in a point like 1, we see that that's going to be positive, and we see that it's concave up, and that's going to be happening always. So here, again, we see at 0, 0, that's going to be whole there. It's going to be concave up always. It decreases from 0 to 1 over e, but 1 over e and negative 1 over e. So let's say this point right here, it's decreasing, it increases, and it hits the x-intercept at 1 and 0, and then it continues on. And so that's what our graph will look like.